Let's talk about common denominators. Why wouldn't we? Common denominators have so many purposes within fractions. Often we think about we need them when we add and subtract, but there's so many other uses for them and reasons why we would want to get them. In front of you here on the screen are two fractions. You can find your own manipulatives that align with those. But what I want you to do is then see if you can find other manipulative bars that would be equivalent to those that have common denominators. So find a way to reproduce these in a way that they would have the same denominator rather than 6 and 4, rather than two different denominators. When you're done, you've probably created something that looks like this, and then those would be those orange bars, those orange manipulatives. What we did here was we took the red ones and we cut them each in half and turned it into 2 over 12. With the blue ones, we cut them into thirds, changing it into 3/12. Now we can see they have the same denominator, right? So that's the idea. That's the idea of getting these common denominators. So let's talk about a number of different uses and reasons and maybe even other ways we go about getting common denominators. Because using this visual method is strongly encouraged, recommended by the National Council of Teachers of Mathematics. They reinforce the importance of these models. So students don't just picture numbers when they see fractions. They're picturing these models. They're picturing the actual sizes of those values. Another way to get common denominators, so to find common denominators, is to use multiples, listing out multiples. In the previous problem, we were working with denominators that were 6 and 4. 6 and 4. I think it was 1/6 and 1/4. And if we need to get those denominators to be the same, one way we can do it is just list out the multiples of both numbers. Multiples. And so maybe we make a column of 6s and a column of 4s, and we just start counting by 6s. So we have 6, 12, 18, 24, 30, 36. And then we do the same thing for 4, and we have 4 and 8 and 12 and 16 and 20 and 24. And then we observe and we notice that we have a couple different common multiples. We have 12s, and we also have 24s. And if we continued the list, we would have more and more. And as we've learned before, the smallest number that they have in common will be the least common denominator. So that would be the least common denominator. There are other common denominators like 24, but we always like to find that lowest one, the least common denominator. So using these lists of multiples is a way for students to learn how they can also build that common denominator. Once you have found it, if we go back to 1/6 and 1/4, and we look at them individually, then we know we have to change this into something with a denominator of 12. And so we use the principle that we talked about earlier in another video of multiplying our numerator and denominator by the same number. We can do that, and it's still an equivalent fraction. And so we notice that 6 times 2 is equal to 12. So 1 times 2 must be equal to 2. And this is our equivalent fraction to 1/6. Similarly, with 1/4, we look to build that new denominator and ask if we can find some factor, something we can multiply by. And we notice that that would be a 3. So 1 times 3 is equal to 3. And again, we have a fraction equivalent to 1/4. Now that we've seen a couple different ways to find common denominators, let's practice. So I'll give you a couple pairs, and your job is just to get these fractions to have a common denominator. So get a common, I'll abbreviate it CD, common denominator. Let's start fairly straightforward. Let's go 3/4 and 2/5. So change those, get those into a common denominator. So what you might have done was look at the 4, the 5, maybe you counted by 4s, 4, 8, 12, 16, 20, and you counted by 5s, 5, 10, 15, 20. Notice those are the common denominator, the least common denominator. So that's one way you could have done it. And then we have to manipulate the fractions. If we're going to change 4 into 20, we are multiplying it by 5, which means our numerator also gets multiplied by 5. So this now changes into 15/20. Similarly, 2/5, we need to change that denominator into 20 by multiplying by 4. That becomes 20. We also multiply our numerator by 4. So we have 8/20. So we have 15/20, and we have 8/20. Again, these fractions represent the same number as their original fractions. It's the same number, it's the same value. Try one more. And this pair is going to be 1/6 and 5/18. Take a moment to do that one. One strategy that I find useful when I'm trying to build a common denominator is I try to look inside each number. I try to look at the factorizations of 6 and 18 and see if I can discover something. One thing I discover with the number 18 is that 18 is equal to 6 times 3. And so all I need to do in order to get these denominators the same is multiply this by 3. This one already has a 6. This one has a 6. This one has a 3. This one needs a 3. And so if you can build your common denominator by using the factorizations of the other denominators, that can be a really useful tool if you get good at that. So we're multiplying this fraction by 3/3 to get 3/18. We don't even need to change this one. It's completely fine to leave one of your denominators just as it is. Now, one of the things that I find lots of students misunderstand is when we start to use signs, negative signs within fractions. And so what happens when we have negative signs in fractions like this, or even out front like that? Those actually all mean the exact same things. Those represent the same value. They have the same sign. They all have one negative. This one happens to be on top. This one happens to be on bottom. This one happens to be out front. And we can even write each of these as this. Negative with the a over b in parentheses. Those all are equal to each other. They're all the same. Now, when you have a negative a over a negative b, and if both of them are negative, well, that's the same thing as just a over b. It's as if the negatives cancel each other out. Now, I think the one that is most misunderstood of all of these that we see right here is that one right there. A lot of times I will see people misinterpret that as the negative going to both the A and the B, and it does not. It can go to either one, as we saw here and here, but it doesn't go to both. So if you have a negative out front like that, it just means that you've got this fraction a over b, and it has a negative value. So those are the rules for signs regarding fractions. Sometimes it might be more beneficial if you have, let's say, this. If you have a fraction with 2 over negative 3, sometimes it might be more beneficial for the problem you're working on, the situation you have, to rewrite it as negative 2 on top, 3 on bottom. Sometimes that could just be better for your situation. So we've been talking about common denominators, and one of the best things it's good for is to test for equality. Test for equality. What do I mean by that? I mean, look at two fractions and determine, are these two fractions equal? Or is one greater than the other? So we're going to spend a few minutes examining that, looking at two fractions and determining which is bigger, or are they equal to each other. So let's take some fractions that it's not completely obvious. 19 over 62 and 8 over 27. And the question is, are those equal? We'll kind of put an equal sign with a question mark. Are those equal? Well, one way you can go about this is to get a common denominator. It's easy to tell which fraction's bigger if the denominators are the same. We know 1/3 is less than 2/3. They have the same denominator. Let's do that here. Now, 62 and 27, that's going to be kind of hard. I think the easiest way we can do that is take the first fraction, multiply them both by 27 on top and bottom, and take the second fraction and multiply them both by 62. Notice that those are the opposite denominators. So this denominator is going to multiply this fraction on top and bottom. This denominator is going to multiply this fraction on top and bottom. And I accidentally deleted my 2. So rather than actually doing the multiplication, I want to show you sort of an intermediate step. Notice that the denominators here and here, no matter what that number is, they're going to be the same. What I care about now are the numerators, these things on top. 19 times 27 and 8 times 62. We already know that the denominators will be the same. So what we really care about are the results of this multiplication. And so if we pull out a calculator and do that multiplication, we will see that, I can pull my calculator over here, and let's make it so we could see the work behind it. We take 19 times 27, 513 here, and we take 8 times, try that again, 8 times 62, and we get 496 there. And so we see that those numerators are not equal to each other. It doesn't matter what that denominator is. We know that because it has the same two numbers, it's got the same two factors, that they are equal. So we can see that these are not equal. Let's go back a second to the original problem though. 19 over 62 and 8 over 27. Notice that what we multiplied here, 19 times 27, was really this. We took this denominator, multiplied it by 19. And this product here was really this times 8, this denominator times 8. So when we are trying to determine whether two fractions are equal, we can use what we call their cross products. Cross products. And there's a nice test for the equality of fractions that says for any fractions, a over b and c over d, a over b equals c over d if and only if a times d equals b times c. A times d is equal to b times c. We multiply up and across, and we compare those products. And if they're equal, then the fractions are equal. If they're not equal, then the fractions are not equal. So let's try. Let me give you a few of these, and you test to see if these fractions are equal or not. We will do 3 of these. We will do 42 over 105 and 14 over 35. The second one we will do is, let's see, -2 over 3 and 2 over -3. And the third one we'll do is 8 over 71 and 5 over 43. Take a moment to examine the potential equality of those fractions. So on this first one, we are going to multiply 42 times 35. When we do that, we find that is 1,470. When we multiply 105 times 14, we find that is 1,470. Those products are equal, so we can say that these are equal. For the second one, we look at our cross products. -3 times -2. -3 times -2. Well, that is equal to a +6, 2 negative numbers. And then we have 3 times 2. Also +6. The cross products are equal, so the original fractions are equal. And did you notice that spoke to what we talked about moments ago? The negative can be on top or the bottom, doesn't matter. For the third one, we multiply 71 times, let's get the numbers right, 71 times 5, which is 355. And we multiply 43 times 8, and we get 344. Those are not equal, which means the original fractions are not equal. Because that's one way that we can assess the equality or potential equality of fractions. Another way we can do that is with a tower of bars that looks like this. I think this is a really great image. I think you can get a lot from just examining this this bar here. One thing that you might also do for this next exercise is you can use manipulatives, but it is probably going to be more beneficial to use the app that is linked in Blackboard. And so that app looks like this. Okay, so I'm going to go back and forth. I'll toggle back and forth between these two screens, at least at first. So the back here, what I want to do is compare two fractions. I'm going to compare two fractions, and they're going to be 4/5 and 7/9. And we're going to put a less than or a greater than sign between those two, 4/5 and 7/9. And so if I go back to that app, notice I already have a 5ths bar and a 9ths bar. They're the exact same length. So we're going to shade them in. Pick a color. So it was 4/5. So on the bottom, 1, 2, 3, 4. That is the visual representation of 4/5. And on the top, we have 7/9. 1, 2, 3, 4, 5, 6, 7. And so you can see there that the green is slightly longer than the blue, which means 4/5 is greater than 7/9. We can put 4/5 is greater than 7/9. So see if you can find a strategy like that, right? You could sketch them, sketch the bars. You can look at this diagram that's in front of you right here, or you can use that app. So try the same thing with 5/8 and 2/3. And then finally, 2/7 and 3/10. I went ahead and did this in that application. And you can see this is a picture of 5/8 compared to 2/3, which means 2/3 is going to be greater than 5/8. So our arrow will point that way. And when we compare 2/7 to 3/10, you can see the blue section, the blue 3/10 are slightly bigger than the 2/7. So that will be 2/7 is less than 3/10. So these visuals, these bars are an excellent way to demonstrate this and for students to start to picture the differences here. So I think this also, I'm going to scroll down and I'm going to repaste that image because we're going to look at just two more nice little relationships here. And on one side, we're going to look at the shaded in colored sections. And on the other side, we're going to look in these white unshaded sections. And so we can look at these descending colored sections here and make this statement that 1/2 is greater than 1/3, which is greater than 1/4, which is greater than 1/5, which is greater than 1/6, and so on and so on. And so a student, once they see that and they start to connect it with these symbols, can start to also make the connection that as long as you're keeping just a unit in the numerator, as the denominator gets bigger, the value gets smaller. The size that's shaded in gets smaller. And that's a really important relationship for students to understand. If we look at the other side, see if you can figure out maybe the relationship that's going on here in the unshaded sections. It's going to look something, but we do this. It's going to look something like this. 1/2, the top one, is less than 2/3, which is less than 3/4, which is less than 4/5, which is less than 5/6, etc. So that's another nice relationship that we can see there amongst those fraction bars. Now, another way to compare to see which fraction is bigger is to get those common denominators. We looked at that earlier, but we're going to just extend that one little bit further. So I'm going to have you look at two fractions here, 5/8 and 3/5. And at first glance, it's hard to tell which one's bigger if you don't already know. So if we get those common denominators, it'll be much easier to tell. So when I look at 5/8 and 3/5, I notice the denominators and I examine them, I try different strategies, and I find out those can both have multiples of 40, right? The least common multiple of both denominators would be 40. So we have to do what it takes to turn them into 40. So I will multiply this by 5 and then that by 5. That changes 5/8 into 25/40. With 3/5, we want to change 5 into 40. So we will multiply by 8. And then, of course, 8 on top. This fraction then changes to 24/40. Now compare the two fractions. They have the same denominators, and this numerator is slightly bigger than that one. So we can say 25/40 is greater than 24/40, and thus 5/8 is greater than 3/5. We can compare those original fractions to each other. Several moments ago, we talked about the idea of cross multiplication as well. We can also use that strategy to compare. I'm going to go back and reuse these same two fractions, 5/8 and 3/5. If we do the cross multiplication here, we have 5 times 5. And if we do the cross multiplication here, we have 8 times 4. This one is 25, and this one is 24. Notice how I brought the bottom up to the other side in both cases. 5 times 5, 8 times 3. I wrote 4 when I meant 3. Let me correct that. 8 times 3. And so notice here that 25 is greater than 24. And weren't those the exact same numbers we had up here? So if you use the cross products of the two fractions and you find that one is greater than the other, that means that will be the same relationship that the other original fractions had. 5/8 is greater than 3/5. It'll be the same. We can state that formally, as we love to, as this test for inequality of fractions. For any fractions, a over b and c over d, assuming that b and d are positive, those denominators are positive, a over b is less than c over d, so this one on the left would be less than if the cross product on the left, AD, notice AD, is less than BC. That's why I said it's important when you're doing this multiplication to bring that 5 up that way. 5 times 5 on the left, and bring this 8 up that way. 8 times 3 on the right. And then the opposite is true if AD is greater than BC. So your final exercise here will be to try that out. Will be to test that. So I'm going to give you 3 sets of fractions, and your job is to place an inequality sign between the two fractions and try this strategy that we just used. Those didn't copy very well. Let me rewrite these for you. So we are going to compare 3/7 and 4/10. We are going to compare 3/4 and 7/9. And we are going to compare negative 3/7 and negative 2/5. So be careful with that one. So let's try this method using those cross products. 10 times 3, actually, I'm not going to draw the arrow in. 10 times 3 is 30. 7 times 4 is 28. We can see that 30 is greater than 28. So 3/7 is greater than 4/10. Over here, 9 times 3 is equal to 27. 4 times 7 is 28. 28 is larger than 27, so 3/4 is less than 7/9. Cross products again. 5 times 3 is 15. 7 times 2 is 14. You may be wondering, but hey, those had negatives. They sure did. So I'm going to put those negatives there. 15 is obviously greater than 14, but it's switched around when they're negative. Negative 15 is less than negative 14. Therefore, negative 3/7 is less than negative 2/5. So I hope you have a slightly better understanding of common denominators, why we can use them, how we can use them, and many different ways in which they're beneficial to us.